Okay, so today we're looking at the bisectors of a triangle, and the first bisector we can look at is called perpendicular bisector of a triangle, which is a line, ray, or segment that is perpendicular to a side of the triangle at the midpoint of the side. So exactly what it says it is. It's perpendicular, intersecting at a right angle, and it's a bisector, splitting it perfectly in half, going through the midpoint. And when we talk about these bisectors, another thing we need to look at is something called concurrent lines, which is any time that we've got three or more lines that intersect at the same point, right? So three or more lines, kind of like an asterisk or something like that, where they all intersect at one point, and this point where they all intersect, that intersection of the concurrent lines is called the point of concurrency. So the three perpendicular bisectors of a triangle are going to be concurrent lines, meaning if I draw in all three perpendicular bisectors in one triangle for all three sides of the triangle, then they should all intersect at one point. And then the location of that point of intersection is going to change depending on what kind of triangle we have. If it's an acute triangle, the intersection or the point of concurrency is going to be on the inside. If it's a right triangle, the point of concurrency is going to be on the hypotenuse, on the side opposite the right angle, so on the triangle there. And then if it is an obtuse triangle, then it's going to be outside the triangle, and the bigger that obtuse angle gets, the farther outside of the triangle it's going to move, which is basically the trend here. The small angles, acute angles, it's inside. The right angle, it's moving towards the outside, it's on the triangle, and then obtuse, it's going outside the triangle. So theorem 5.5, the concurrency of perpendicular bisectors of a triangle. So the perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of the triangle. So if I put in all the perpendicular bisectors, which is the blue lines here, then all of those perpendicular bisectors of the triangle are going to be equidistant from the vertices of the triangle. So point P is going to be the same distance from B as it is from A and as it is from C. So PA, PB, and PC are all going to be congruent. So, and then a name for point P, or this point of concurrency of perpendicular bisectors, is the circumcenter of this triangle. Okay, so point P here is the circumcenter, and that's because since it's the same distance from every vertex, if I extend a compass, put the point at P, extend it to one of these vertices, and draw a circle, we can create a perfectly circumscribed circle. Circle meaning on the outside of the figure. So the circumcenter, that's the center of a circle that would be circumscribed around the triangle. All right, so here we got a problem where it says three people need to decide on a location to hold a monthly meeting. They'll all be coming from different places in the city, and they want to make the meeting location the same distance from each person. And when I want to explain why using the circumcenter as the location for the meeting would be the fairest for all, and I've already got the answer written out here. It says the circumcenter will be the same distance from all the vertices, remembering that the circumcenter is equidistant from each vertex. And since each vertex represents each person, so I've got a person living at point A on the map, point B on the map, and point C on the map, then the circumcenter would end up being the same distance from each person. So wherever that circumcenter ends up inside here, that would be the same distance for each person to travel, so they all travel the same distance. Alright, so B wants us to locate the circumcenter and then tell what segments are congruent. So locating the circumcenter means that we actually have to construct the perpendicular bisector for each side. And so go through that process here, and we'll go through the process in more detail later on because we're going to cover all the constructions after this chapter. But so in order to construct the perpendicular bisector, we put the point at one endpoint, make sure our compass is wider than half the distance between the two endpoints, and then we're going to make an arc on each side of the line. Then we go to the other endpoint, put the point at that endpoint, and we're going to make an arc that will intersect the arc we just made. And I'm going to go ahead and, well, I've got the compass, go ahead and do that for each side. So make an arc above and below on each side. Above and below on each side. Once I've got all of those in place, then I can bring in my straight edge, line up with each of the intersections. On there. Up right there. There we go. And remembering, if you do it right, which I'm a little bit off here, but all of those perpendicular bisectors are concurrent lines, which means that they should intersect at the same point. I'm going to clear off all this extra. Make it a little bit cleaner here. And I'm going to go ahead and label this as point P. And so basically, if there was a restaurant or something in this area on the map, then that would be the best location for all three of those people to meet. And the question continues on to say, what segments are going to be congruent? Well, if I went ahead and drew in a segment from each of the vertices to point P, then each one of these segments should be the same length. And so The segments that are going to be congruent would be AP, congruent to CP, congruent to BP. So then angle bisector of a triangle, it's going to be a bisector of an angle of the triangle. Remember, a bisector of an angle just splits the angle perfectly in half into two congruent angles. And then the incenter of the triangle is going to be the point of concurrency of the angle bisectors. And the three angle bisectors are concurrent, meaning they're all going to intersect at one point again. And the incenter of the triangle is always inside the triangle. So incenter, where all these angle bisectors in blue intersect, would be the incenter. And it's the angle bisectors of the triangle intersect at a point that is equidistant from the sides of the triangle. So in this case, the lines come from the vertices, and then the point of intersection is equidistant from the sides. And remember, with the perpendicular bisectors come from the sides and meet in the middle, and then they're equidistant from the vertices. So these are just kind of the converse of each other. And then since the distance to each side is the same, that distance could represent the radius of a circle that we can inscribe in the triangle. Inscribe meaning inside the figure. So that's the incenter, the center of an inscribed circle, whereas the perpendicular bisectors was the circumcenter, which is the center of a circumscribed circle. So the angle bisectors of triangle XYZ meet at point P. What segments are congruent? And find the length of PT and the length of PV. So the angle bisectors are blue, splitting each angle perfectly in half and meeting at point P. So that makes P the incenter, and the incenter is equidistant from the sides. So these lines going to each side would be the same length or congruent. So PT would be congruent to PV, would be congruent to PU. And then lastly, it wants us to find the length of PT and PU, or PT and PV, sorry. So PT, PV, we just said that they're the same length, they're congruent. So if I can find the length of one, then I know the length of both of them. And then in this picture, they give me two measurements. They give me 12, the distance from T to Y, and 13, the distance from P to Y. Which if I look here, this blue line, the red line, and then this line of length 12 here creates a triangle. And more specifically, since this intersection is a right angle, that means this is a right angle. And so we've got a right triangle. We've got two sides given to us. And so in order to find the third side of a right triangle, we can use Pythagorean's theorem. Which says that a squared plus b squared equals c squared. And the thing you have to remember is that A and B are the legs of the right triangle, and C is the hypotenuse. So when we look here, they gave us 12, which is a leg, 13, which is a hypotenuse. So when I put those into the equation, I'm going to have a squared plus the leg, 12 squared, plus the hypotenuse, or equal to right at the same time. So a squared plus 12 squared equals c squared, which is 13 squared. Now it's just a matter of solving for a. So a squared plus 12 squared, which is 144. It's going to equal 13 squared, which is 169. Subtract the 144 from both sides, and we get a squared equals 25. And to find the actual length of a, then we have to take the square root of both sides. So a equals 5, or in this case, a represents PT, so that's 5. And since PT is 5, PV is 5, and for that matter, PE would be 5 as well. So PT equals PV equals 5 units. All right, so that's everything.